Well, good sunny Michigan afternoon to everyone. I was taking some pictures at my summer job at the parks this week, and some of you may have seen them on Facebook. The one picture I took here was at North Beach Park, and it's a beautiful picture of the sun behind the tree there with the sky. And that kind of got me thinking that maybe this was a good opportunity to do a quick little physics lesson, because I know you're all missing physics so much, or are excited to take physics in your future maybe. And so the question that came up is, why is the sky blue? And some of you know the answer to that question, and some of you don't. So I thought it might be fun to try to explore that a little bit. But I like this picture. There's just the differences in the sky here. You've got this storm approaching to the north here, but you can still see the blue sky. But notice how the sun itself appears to be white. Why is the rest of the sky blue but the sun appear white? If I pull up another picture that I took, here's a picture, I believe this was the next day, and this is at sunset. And you can still see a little bit of the sky is blue, but why are sunsets orange and why are they red? So we want to explore that idea too. No thank you. So we will call upon our friend here, Mr. Hewitt, to help us explain. But before I get there, let's take a look at this. So why is the sky blue? And it goes through the lingo here. It says the results of selective scattering of smaller particles than the wavelength of incident light and resonates at frequencies higher than scattered light. And a lot of us are like, say what now? So let's take a look at the picture here. The incident beam is the light wave approaching a particle in the atmosphere. And it does travel as a wave. And what happens when it hits, say, a nitrogen molecule or an oxygen molecule when it's in the sky? And these green arrows represent scattering of light. And so when we talk about why is the sky blue or why are the sunsets red, what we're dealing with is actually light scattering. And we're going to let Mr. Hewitt kind of give us a little further explanation of that. So we will pull him up here.
You ever be wondering why the sky is blue? How many say, well, it's probably the reflection of the water. All right, now go to Minnesota. Now go to Kansas. What's the color of the sky in Kansas? Well, it's usually yellow-green, right? Come on, what is it, gangs? It's still blue. Why is the sky blue? A little bit different phenomenon going on here. Let me just tell you about it. It turns out that light coming down from the sun, boom, showers itself upon the atmospheric molecules. Now we got big ones, we got little ones, we got all sizes up there, okay? And these molecules will scatter off the frequencies of light. It's called scattering. Now, what frequencies will be scattered? Let me give you an example. Let's suppose I have a couple of bells here. Here's a little bell, and here's a big bell. When I disturb these things, they're going to scatter sound off in all directions, and what will the sound be, high pitch or low? Let's try the little one right here. Boom. You hear that? Now let's try the big one. Did I have that right? How many say I got that wrong? Wrong. No, that's completely wrong. It turns out the little bell will bing, and the big bell boom. Isn't that true? Guess what behaves the same way up in the sky? The what? Molecule. What do you suppose the little tiny ones will ring? High frequency or low frequency? High frequency. How about great big ones? Low frequency, okay? Now, what are the size of the molecules in the sky? Large or small? Begin with an S. Small. And then nitrogen and oxygen mostly. Isn't that true? O2, N2. And when that sunlight comes beating down on those things, it scatters off. Light scatters off. And it turns out the color of the sky is the color of all those little bells, or all those little optical tuning forks, or all those little vibrators. And they're vibrating at mostly what frequencies, gang? High frequency. How many know what high frequency looks like to the human eye? Blue. And higher frequency, even violet. Let me tell you something. The sky really scatters off more violet than it does blue. But you know what? We're not so good at seeing violet. We're a lot better at seeing blue. So guess what our eyes tell us the color of the sky is? We give you the B. You could have done that without the hint. Okay? And it's blue because the tiny, tiny particles are scattering off the high frequency. So we see a blue sky. Okay? Interesting enough? Now you look straight up at the sun, straight up above. You see the sun white, yellowish white. Okay? Okay, a little bit of filtering coming through, but not very much. How about at sunset, gang? At sunset, when you look at the sun, it ain't white anymore. And you say, well, it's sort of like an orange, but there's probably no reason for that. It's just characteristic of sunsets and sunups to be orange. How many already see why it is that the sun is kind of orange at sunset? Let's take a look. Is the earth here? Here you are, standing right here. Here's the sun at noon. Somehow light comes down, hits the air, scatters off to your eye, scatters off to your eye, and you're seeing what mostly scattered is blue. So you look up and you see blue all around. But when you look directly at the sun, that white light, boom, overwhelms the little bit of scattering going on, and you see a white sun, whitish. Okay? So at noontime, boom, you see the sun whitish, huh? How about at sunset? What happens at sunset? Can we do this? We can do this experimentally. We can do this experimentally. I'll tell you what. Let's just do it right here. Here's the atmosphere of the world right here. It's the atmosphere of the world. Huh? No. Let's do it this way. Here's the atmosphere of the world. And here's the sun. Now the sun. Red, orange, yellow, green, blue, violet. Okay? Bing! What do you guys hear? Well, let me just do it now. Do it again. Red, orange, yellow, green, blue, violet. Bing! What do you guys hear? White. Do you hear white? Huh? All the frequencies together give you white. Isn't that true? Right? So you hear what? What color of the sun? You give me the W. And with it. Try it. White. All right? Whitish anyway, all right? White sun. All right. Here's our atmosphere down here. The atmosphere. These tuning forks. Blue, 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 violet, violet, blue, blue, red, blue, blue, pink, blue, blue, chartreuse, blue, blue. Get the idea? What's happening? I'm taking a ring all these. Ring! What do you guys hear? Blue. You all heard blue. That's right. Now just a little bit of red in there, yeah? A little bit of green in it. But mostly rough, blue and violet. And you heard blue, yeah? Okay. Let's try the sunsets. Can I have a volunteer? Make one. Put your ear right down here. And I'm going to hit these tuning forks. No, right behind. I want to go right there. I'm going to hit these tuning forks. This is the sun, 150,000 kilometers away, and the sunlight going to come down to the atmosphere, boom, and Mater's standing on the ground, and here's the sky between her and the sun, yeah? Here we go. We do by experiment. One of the beauties of science is you do by experiment, huh? You don't just do it all in your head. Here we go. Bing! Oh, first of all, I should say this. You guys get the white again. Let me put a reflector here. So all this beam energy goes down here. And this beam energy is going to scatter off here. All right? Okay. Bing! What color you guys hear? Blue. Did you hear blue? You all got it? Good. Madro, what color did you hear?
White?
Yeah, she heard white. Why'd she hear the white?
Because she's sitting right next to me.
That's right, honey. Some filtering behind you, but she could have come right at her. It's a good thing you didn't have your eyes there. Just get your ear in there. Just get your ear, okay? You heard a white, isn't that true? Okay, here we go. Okay, right like that. Now, we are at sunset, gang. Sunset. All right? Air is thicker, huh? Bing! What color are you guys here? Paul, would you pass out the Q-tips? Let me remind you, we got blue, 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 red, blue, blue, chartreuse, blue, blue, red, blue, blue. Okay. All right? Reminder? Huh? All right. Maybe put your ear right behind you. You can even put your eye now, sorry. What color you guys here? Blue. What color you here, Meadow? Yeah, all right. Meadow right here. Right here, right here. Beautiful. Great. You've been a sport. Hey, is this not neat? Is this not neat? At sunset, of course you're going to see orange. Because at sunset, that light's coming through many, many, many kilometers of air. And what color is being scattered out all along? Blue. Blue is coming. All these people looking up seeing the blue sky. They're seeing the blue that you would have got to you. And by the time that light gets to you, and it's all tuckered out in high frequencies. Almost no high frequencies left. And so what finally gets to you? High or low? Low. And so it turns out the atmosphere is transparent in low frequencies, but not so much to the high. The highs are scattered. And that's why you see the nice colors at sunset.
All right. So that does a pretty good job of explaining what's going on. So we can see that the sky is blue because as you're standing on the surface and the light waves are approaching you, blue light's kind of being scattered scattered out by the oxygen and the nitrogen molecules in the atmosphere, and so you're seeing blue all over the place because it's being just tossed out of the sun's rays. Now, if we use this animation here, you can see that the sun itself would be white because it's sending off frequencies of light towards you. So he kept mentioning, red, green, blue, indigo, violet. All the Leroy G. Biv colors, frequencies are being sent your way. So if the sun is somewhere over in this area here, and then you're standing right there in the equator, and you are apparently very tall to scale the Earth, a lot of the wavelengths are still reaching you, and that's why the sun looks white, as we saw in that first photo I showed you at the beach at the beginning of this video. Now, as you are kind of getting more of an angle towards the sun's waves, you're starting to get a little bit more blue light scattered out, and so you don't see as much white, you see a lot more blue. The blue is just being tossed all over the place, and so you can see lots of blue. Now, sunset. Notice, well, first of all, notice all these little blue molecules or blue dots being scattered, representative of why the sky looks blue here. Look how many more are being scattered as you are at more of an angle to the sun now. Boom, all over the place. All these blues and even the greens and some of the yellows are just being scattered all over the place. So if you had a friend that was still staying here, they'd still see all this blue. But look, by the time it gets to you here, look all the colors that are reaching you. It's mainly the reds and the oranges. And so if we can see down here, this is what the sky would look like to you if you were standing there. So when we have sunset, or even sunrise, this is the same thing that's happening. Except at sunrise, the sun would be to the other side of you. So the sunset, the sky appears this color to us. During the daytime, you can see the color is more of a blue, or even a white if you look directly at the sun there. So I think that's pretty cool. Hopefully it didn't ruin sunsets for you, but we can see that because of light scattering and the fact that the blue wavelengths of light that wavelength is so small that it's very easy for it to get affected by small molecules and run into those small molecules and to be scattered off, that by the time the sun's rays pass through all that atmosphere at sunset, there's no blue left. But those red and orange lights, those wavelengths of light, have a much longer wavelength, and they're able to kind of snake through all the air molecules, and they're not as affected by scattering. And so they're all that's left by the time the light reaches your eye at sunset. I'm going to close this here, and let's do a little review. For those of you who've had physics class, you're familiar with checking your neighbor questions, or in this case clicker questions. So we'll use these as review here. The redness of a sun up or sunset is due mostly to light that hasn't been, your choices are there, A, absorbed, B, transmitted, C, scattered, or D, polarized. Correct answer is, make your guess now, scattered. So what we've been talking about all along has been light scattering. So let's just go to a review there. The blueness of the daytime sky is due mostly to light. Again, and scattering. The color of light that passes most readily through a thick atmosphere is it red? Is it white? Is it blue? Or is it violet? Remember that this question is asking what is most likely to pass through a thick atmosphere, not what's most likely to get scattered. So the correct answer is red. No still. When relatively large particles contribute to the mix of particles in the sky, in the atmosphere, the sky is bluish, reddish, whitish, or greenish. The correct answer is whitish. If the molecules in the sky scattered low-frequency light more than high-frequency light, the color of the sky at noon would be red, green, blue, or white. Keep in mind that this question is kind of one of those what-if questions, and it's saying, what if the opposite were true of what actually happens? So we know that light actually scatters the atmosphere actually scatters high-frequency light and not so much low-frequency. This question is asking, what if the reverse was true? What would the sky look like? And the correct answer would be red. So as you can see, there's a lot of physics that goes on when it comes to sunsets and the color of the sky. So I'll leave you with one more picture here. So this is a beautiful picture of sunset out in Grand Haven a couple years ago that I took. So now we have a greater understanding for why the sky looks the color it does.